Hello everyone, I'm Dr. Poonam Yadav. I'm a lecturer in the Computer Science Department at University of York, UK, and I'm also ACMW UK Chair. Today I'm going to talk about the booting process in an operating system. We all have heard the word operating system quite often, and we use many operating systems such as Windows, Linux, Mac OS in our laptop or desktop machines. We also use Android and iOS on our mobile phones every day. Therefore, in this lecture, I'm going to discuss the booting process, which is a step-by-step starting process of an operating system in more detail. And I hope this will help you understand what happens behind the scene when you switch on your machine. In this lecture, my focus will remain on the Linux-based operating systems, but the procedure is quite similar for other operating systems as well. This presentation is targeted for first year or second year computing-related undergrad students, but I think it's useful for everyone who is curious and interested in knowing a little bit more about computing fundamentals. So before we start and understand what is the booting process let's have a look on the basic computer organization and working flow. To give you an idea of a computer on a single board, I have taken a Raspberry Pi P4, which is a single board computer. It's a quite powerful 1.5 gigahertz 64-bit quad-core ARM processor from Broadcom, and a number of input-output interfaces such as USB-C, USB 2, USB 3, gigabit Ethernet, micro HDMI ports. It also has SD-RAM and a SD card connector for non-volatile memory used for storing operating system and data. On the right-hand side, I show a simplified architecture of a CPU. Has a processor and a control unit. The processor itself has a number of registers which holds the data temporarily, and an arithmetic and logic unit which performs function on register data. As we know, for processor to do any operations on the data in program has to be in the memory. So that memory management unit fetches this data to the registers and allow ALU to do the operations and then store the process data back to the memory and to the permanent storage to the ALU to the output interface. So this provides you a bit of data flow in the computer and the different components such as input and output interfaces. Let's go back to and resume with our understanding of the bootstrapping process, which means starting process of an operating system on this machine. What happens when you switch on your computer? As soon as you press the power button on your laptop or desktop computer, it starts working. The motherboard sends a signal to the power supply. After receiving the signal, the power supply provides the proper amount of electricity to the computer. When the computer motherboard receives the power good signal, it tries to start the CPU. CPU resets all leftover data in its registers and set predefined values to each of them. The code segment register points to the reset vector. It is a non-volatile memory location. Please note, it's a non-volatile memory location at which the CPU expects to find the first instruction to be executed after reset. So this is a part of the firmware. It contains a jump instruction that usually points to the BIOS, basic input and output system, or in many modern computers, it is UEFI, which is Unified Extensible Firmware Interface. So before we look at how the booting process goes ahead from the BIOS, let's quickly revise what is BIOS, why a computer needs it. So what is BIOS? Originally, BIOS firmware was stored in a read-only memory chip on the PC motherboard. In modern computer systems, BIOS contents are stored on flash memory, so it can be rewritten without removing the chip from the motherboard. It is the first software to run when computer is powered on. There are a number of BIOS functions. We are listing their main 4 functions here. First function is integrity check. When you turn on the computer and when BIOS is running, the first function it does is a power on self-test. It tests the computer hardware and makes sure there are no errors exist before loading the operating system. What that means, it checks that hard drive is reacting properly. It can check if read-only memory functions well. It checks whether your arithmetic and logic unit and all the registers are working fine. There is no problem there. Second part is the bootstrap loader. Role of the bootloader is to locate the operating system. If a capable operating system is located, the BIOS will pass control to it. We'll be looking at this in a little bit more detail later because that's the main bootstrap loader plays a main role in the booting process. And then BIOS drivers. BIOS drivers are low-level drivers that gives the computer basic operational control over computer hardware, such as keyboard, screen, mouse, serial port, etc. BIOS drivers allows user to use computer input-output resources even before OS is loaded. For example, screen, keyboard, mouse, or access to hard drive. And the fourth one is BIOS setup and CMOS setup. These are the configuration programs that allow you to configure hardware settings, including system settings such as computer passwords, time, date, etc. It could be basic GUI or a command line input-output interface. So all these pieces of software are called firmware, as these are provided by the computer manufacturer on the non-volatile memory, either on an EEPROM or a flash. So let's look in a little bit more detail on the BIOS bootstrapping process now, because we now understand what is BIOS, but how BIOS help us in the bootstrapping process of operating system. As a part of BIOS post-process, BIOS scans the input-output buses for attached hardwares. It identifies and maps access to the hard disk you have connected to your computer. BIOS on the newer motherboard is smart enough to even recognize and identify USB devices such as external drives or USB mouse, letting you boot the USB from USB sticks or use your mouse in a legacy software, which is a very powerful because previously we were very dependent on operating system to recognize these drivers and recognize these USB devices, but now this functionality has been embedded in the BIOS itself. Second is like BIOS setup stage. User is normally presented with an option to quickly hit a key to enter the BIOS setup, from where you can configure hardware settings and control your how your PC boots. If you choose nothing, the BIOS will begin with the first step by actually booting your computer with the default settings. BIOS detects and maps connected hard disk and loads a very small program from the first hard disk to the memory and tells the CPU to execute its content, handing off control to the computer. The hard drive is known as the boot device or startup disk or a drive 0 and can usually be picked or set up in the BIOS setting. And I think get a bit more complicated. First is, if there's no boot device detected, what will happen? You may encounter this problem sometimes when you have failed hard drives and your system say they haven't found any boot device and cannot boot further. And second is, how does my BIOS firmware know where to find the OS related programs on the boot drive? So let's have a look in more detail. So the boot device. The BIOS detects the master boot record or UEFI on every disk. Let's start with MBR. The BIOS loads the first 512 bytes from the hard drive to the selected boot device. These 512 bytes are what is commonly known as MBR, or master boot record. MBR is the first and most important component of software side of things in the boot procedure of the BIOS-based machines. Every hard disk has an MBR, and it contains several important pieces of information. MBR is always located at the first sector on every disk. The location is always track cylinder 0, side head 0, and sector 1. If you look at the MBR, it has 3 components. Let's have a look on more details in these 3 components. The first component is partition table. It is index of up to 4 partitions that exist on a same disk. It's kind of a table of content. We will be looking in next slide what is partitioning of a disk or a partition table is. Second is a bootstrap code. This is the first 440 bytes of MBR is a bootstrap code that is often named as a first stage bootloader. The bootstrap code segment of MBR to look up to the partition table of MBR for a partition marked as a active as it searches for the stage 2 bootloader and load the code to the memory for execution by the CPU as the next link in the bootload chain. You can imagine that 440 bytes are not a big data or big piece of a code. It's just have a simple 1 or 2 instructions which only points where to find the next bootloader. The boot signature. The final 2 bytes of the 512 bytes of MBR are called the boot signature and are used by BIOS to determine if the selected boot drive is actually bootable or not. On a disk that contains the valid bootstrap code, yes, the last 2 bytes of MBR should always be hex 55 hex AA values for the 2 bytes. If the last 2 bytes of MBR do not equal to the hex 55 hex AA, respectively, the BIOS will assume that disk is not bootable and is not a valid boot option. In this case, it will fall back to the next device in the boot order list, which you configured in the BIOS setup. Okay, let's have a look at the boot flow. BIOS and memory represent the CPU. On the right-hand side, different components represent part of the hard disk, bootable disk. In the first step, BIOS code points to MBR and loads 512 bytes long MBR to memory. 512 bytes of MBR contains bootloader, partition table, and boot signature. And then CPU from the memory runs the first stage bootloader code. And from the first stage bootloader, CPU reads the active partition and points to active partition address in the disk to load further 512 bytes into the memory. The first instruction in this 512 bytes is a jump instruction, which tells where to find the second stage bootloader code. Let's have a look again at the partition boot sector, this part. In the next slide. The MBR bootloader stage 1 loads the first 512 bytes of the active partition into the memory and instruct the CPU to execute them. So these are you remember first stage BIOS read the 512 bytes of MBR, then from MBR it reads the first active partition pointed by the partition table. And from this, it points to again for the 512 bytes of the address specified by the partition table. And the very first 3 bytes of this 512 partition boot sector contains a single jump instruction, telling the CPU to skip a number of bytes ahead and execute the next stage of the bootload from there. The CPU follows the jump instruction and seeks to the beginning of the bootstrap code contained within the partition boot sector and starts to execute. So now we know the BIOS is outdated, but still works in many machines and replaced by UEFI, which is Unified Extensible Firmware Interface in the new machines. So let's have a look how the booting process works in UEFI-based machines. Before that, let's have a quick overview on what is UEFI works. It is a new model for the interface between operating system and firmware. It has support for reading both the partition table as well as file system, which is quite powerful because we remember there's no way BIOS could understand what file system is on the drive. So it's definitely a useful feature in the EFI. UEFI does not launch any boot code from master boot record, whether it exists or not. Instead, booting relies totally on a boot entry in non-volatile RAM. UEFI launches EFI applications, for example, bootloaders, boot managers, UEFI shell, etc. These applications are usually stored in files in EFI system partition. Each vendor can store its file in the EFI system partition under /EFI/vendor name folder. The application can be launched by adding a boot entry in the NVRAM or from the UEFI shell. The firmware looks for EFI system partition on the disk and tries to find an EFI application in the fallback boot path, which is \EFI boot EFI or boot IA32 EFI on systems with IA 32-bit UEFI. This is how UEFI bootable removable media works. The firmware launches the EFI application. This could be a bootloader or a Unix kernel itself using a EFI stub. It could be some other EFI application such as UEFI shell or boot manager like systemd, boot, or ref-ind. Backward compatibility. Because UEFI is a new system, there are lots of machines which still have MBR or BIOS-based systems, and there are lots of hard disk or hard drives comes with the MBR sector. We need some kind of intercompatibility among these systems. So UEFI provides a backward compatibility with legacy system by reserving the first block sector of the partition for compatibility code, effectively creating a legacy boot sector. The UEFI specification has support for legacy BIOS booting using the compatibility support module, CSM. If CSM is enabled in UEFI, the UEFI will generate CSM boot entries for all the drive. If the CSM boot entry is chosen to be booted from, the UEFI CSM will attempt to boot from drive's MBR bootstrap code. It's a very powerful as compared to BIOS because now it could enable multi-booting of UEFI. If you remember, many of us who has experience of multi-booting a system a couple of years ago in a BIOS-based system where we always needed a main host system, it means one of the operating system boots always first, that triggers the booting of the other operating system. However, using UEFI, you don't need that anymore. What you need is it's a simple configuration manual, which allows you to choose one of the operating system, 1 or 2 or 3 of the operating system, and you can boot one of them at any time on a single machine. Since each OS or vendor can maintain its own files within the EFI system partition without affecting the other, multi-booting using EFI is just a matter of launching a different EFI application corresponding to a particular operating system's bootloader. We'll be looking at how this file system exists in our system later in the slides. This removes the need of relying on the chain loading mechanism of the bootloader to load OS. So we are talking a lot here, boot managers and bootloaders. So let's have a look, what are these two components? Boot managers present a menu of the boot options or provides some other way to control the boot process. The user can then select an option, and the boot manager passes control to the selected tool, or for example, selecting an OS in the multi-booting computer. Whereas a bootloader handles the task of loading an OS kernel into the memory, often along with the support files such as Linux, initial RAM disk, init or file system starting with the kernel running. Some of the useful bootloader or boot managers look like this. I have definitely worked with Grub. Grub is a bootloader. Refind is a boot manager. So I'm looking at what kind of firmware support do they have and what partition table do they support. So we have two kinds of partition table. One is MBR, which is master boot record partition table, and one is a GPT, global partition, UUID partition tables. Have a look on these ones. Here's the link and you can look on a little bit more details about them. So let's come to the partition, because now we are talking about a lot about partition and what is a partition table is in the drive, and we have different kind of partition tables and how I can edit the partition table, what does kernel know about the partition table, and why partition types are important for booting process. So let's have a look on MBR partition table. We remember master boot record, which has a partition table in middle, which was 64-byte partition table. It means allows only 4 entries in that partition table, and every partition table index was 16 bytes long. If you remember, these 16 bytes represent like this. It tells us whether this particular partition is a bootable partition or not, if by setting that byte value. Then starting head, from where this partition starts in the disk, what are the sector, starting cylinder, system ID, ending head, ending sector, ending cylinder, relative sector, and which is important, and total number of sectors in this partition, which provides like total size of this partition is. Because these partitions need not to be equal size partitions, so we need that kind of information for a disk, which is partitioned into 4 logical partitions. Have a look on the disk partition and disk itself, how you read a disk. And then partition table continued GUID partition table, which is called GPT partition table. You remember we have one partition which is called EF5 partition, which is supported by UEFI, and in this partition, the first 512 bytes are protected MBR. So still have this first sector is reserved for MBR, and after that primary GPT header, and then there are different partitions are there depending on how many GPT partition head entries you have. Remember in MBR, there was only 16 byte index were there. Here is a 128 byte index for each entry, each partition entry. So partition type GUID, which is 16 bytes, then 16 byte is a unique partition GUID, then first LBA, and last attribute flags, which are 8 bits, and then partition name itself, which is 72 bytes. We didn't have any partition name in the MBR. So file systems. And now we have talked about the partition. It means if you have a full disk or hard drive, you can divide that into a number of partitions, and each partition is a logical partition which behaves like exactly a new disk to you, even though they actually in hardware all exist in the same machine, same drive. And that's how your operating system, that's provide a kind of protection and security, because you can install one operating system and one file system in one partition, and other operating system holding a different partition or file system second, and they work quite independently to each other without accessing each other's code or shared data or shared memory. File systems. What is the purpose of the file system? What are the different types of file systems? And how do I know what file system on disk I have? These are a part of the booting process, but it plays an important role in understanding the booting process. File system controls how data is stored and retrieved on the disk or a partition. The structure and logic rules used to manage the groups of the data, and their name is called file system. The file systems are designed for flexibility, performance, size, and underlying hardware and OS support, and broadly categorized as disk file system, distributed file system, or special purpose file system. So disk file system, we were reading about disk file systems. Disk file system was usually block-oriented. Files in a block-oriented file systems are sequence of blocks, often featuring fully random access, read, write, and modify operations. These are the different extensions of file systems you have come across. EXT is extended file system designed for Linux systems. X2 is second extended file system designed again for Linux system. ext3 is a journal form of extension 2. ext4 follows the x3 plus journal file system with support of extents, and then versioning file system form of the extension 3. So you could, because this lecture is not about the file system at all, maybe we will have another lecture following the file system, and where we can explain and understand a little bit more about all those systems. The reason I have put these slides here is to understand that different operating systems have a different priority of file system. Like if you can say extension 1 is a Linux file, works very well with the Linux file operating systems, but for example Mac OS 8.1 and above, including Mac OS, all work with Apple's HFS or Apple file system and next generation file system for Apple products, whereas Windows or Microsoft operating systems generally work on NTFS, which is a new technology file system. Traditional systems, mostly systems work on with a FAT, which is a file allocation table. Okay. Options, a modified version of FAT system that used in original exports. There are loads of hundreds of other file systems are there, and our different file systems are supported by different operating systems. Not all operating systems support all kind of file systems. So you have to understand also when you're using any of operating system, what kind of file system it could be supported with that operating system. Then there's a distributed network file systems. For example, MapRFS is a distributed high-performance file system that exhibits file, table, and messaging APIs. Network file system, originally from Sun Microsystem, which was, I think, acquired. Sun is acquired by Oracle a couple of years ago, and is the standard Unix-based systems. NFS may use Kerberos authentication or a client cache. Network core protocol is a novel-based network-based netware, server-based block. They are different. So showdown virtual file system. This is one we are quite interested for this tutorial is DevFS. A virtual file system in Unix-like operating system for managing devices on the fly. So everything in an operating system in Linux is a file system. I have to fit into a file system. Debug file system is a virtual file system in a Linux for accessing and controlling kernel debugging. ProxFS is a pseudo file system used to access kernel information about processes. Temp file system in memory temporary file system or on Unix-like platform. Spec file system is special file system for device files. And system file system, sysfile.fs is a virtual file system in Linux holding information about buses, driver, firmware, or file system. So how do I know what file system on the disk I have? And also, how maybe you can use mkfs command and check what kind of file systems you have, or disk utility that will give you a file system. One other important consideration I have is Mounting of a partition or a device in a Linux file system. This is a very important, because we said UEFI system can detect the file system and it looks for in that particular slash EFI slash that directory where it looks for the bootloader. So that's the whole reason we are just trying to look into the file system here. Unix-like operating system create a virtual file system which makes all the file on the devices appear to exist in a single hierarchy. This means in those systems there is only one root directory. To gain access to files on another device, the operating system must first be informed where the directory for those devices should appear. This process is called mounting a file system. For example, to access the file on CD-ROM, one must tell the operating system, take the file system from the CD-ROM, make it appear under such and such directory. So it's called a mounting of the mounting process. So for example, if I have or USB drive or something, it mounts the USB drive. First, it mounts the device and in a file system so that at least I can access that device. So it will be generally goes in a slash media under DAV or something, that device, or TTY or something like that. And then you tell to access the file system within the device, you tell, okay, mount that file system at slash home slash my drive or my something and slash, and then you can see the whole file system which exists in your system. So let's have a look on a file system hierarchy standard and how does it look in my computer. The file system hierarchy standard defines the directory structure or directory content in the Linux distribution. It is maintained by the Linux Foundation. The standard define many Linux distribution comply with it, but it's not a rule that everyone has to exactly follow the standard. There are some deviations from this. So, but this is a general rule like that. So if I go and my Windows is running on this and I did a command like 3 minus TLL on, if you do it and if go in a machine name, there's a no 3 packages installed, you just get apt-get install 3 and then you can run this command. And I minus D, I give a depth of 1 and I can see I have bin, boot, CD-ROM, DAV, etc, home, lib 32, last found, media, all these files under my slash, under my root directory. If I do that similar command, for example, ls minus la slash in my MacBook, I could see the different directories like this, which is slightly different, but this shows half the directories. Or even if you create a new directory on this path, that appears as a slash test folder. File system table. So now because we have a file system in the system, we also require a file system table so that my operating system knows and find out where, when we search for a file, where that file is. So what is the file system table? How do I edit the file system table? And how do I know if the file system table is working? So let's have a look at Linux FSTab. FSTab in your operating system is a file system table. FSTab is configured to look for specific file systems and mount them automatically in a desired way each and every time. The FSTab file located at /etc/FSTab in Linux-based systems. So if you remember, in a Linux-based system, according to file system standards, all /etc keeps all the configuration files. So if you're looking for any configuration file in Linux-based system, these static files should be, and all configuration files should be under this directory. So it's a static file information system. If you look at this one, there's a UUID, which we remember is a unique ID with any partition in your system or a device. And this file system, for example, what it mounting is it mounting my hard drive on /dav/nvme01 n1 partition 5 during the installation, because I have Ubuntu installed in partition 5. And then it also have /boot/EFI when you look into this one, which says where is my EFI folder from where it should read the EFI configuration load during the booting time. So it's a boot/boot/EFI, which is mounted on a which is type of extension, and it's mount on a particular at this point of time, and at this particular UID is this type, and it is mounted as /boot/EFI. And it is a VFAT, virtual FAT system. UMask is this, and a set of other options are there, which are not necessary for this lecture, but we could look into later on. So locating bootloader and boot manager in Linux file system. So I looked into particular boot EFI, as we knew or looked into earlier in EFI systems. The boot manager reads the bootloader from this particular file system. So I was just looking what is there in my system. So I could see when I look into this, I have three folders. One is under this EFI is Apple. It means in my system there are two. In the same machine, I have also like Mac OS, which is from Apple. I have a boot, which is a by default option, and which corresponds to generally Microsoft booting process. And then I have a Ubuntu, which is boot x64 CSV forward grub file, and I have a grub x64.efi as a grub, and there are other shim x65, couple of bootloaders here files. When I did the same 3DLL with the deft2 within the EFI, I could see this one did with 2BF2. So this gave us a bit of idea why we were looking at all the file systems, because these are necessary for loading and finding where is my bootloader. There's a little bit more information we need to look into, that how these file systems are being mapped and being read, and we could look into that later. So the last step, what happens once the bootloader, for example grub, loads the kernel into memory, kernel extract itself from the compressed version of the file. Kernel will load kernel modules first, and then detect hardware, floppy drive, disk drive, network adapter, etc., and verify hardware configuration, and then scan and load device drivers. At this stage, kernel will mount the root file system and system files. The location of the system file is configurable during the recompilation or other program. If the mount fails, a kernel panic will occur and system will freeze. And to prevent this, we have this init RD, which is like along with the kernel, UEFI system also loads initial RAM disk image, which prevents the kernel from that freeze. After the kernel has extracted itself and started running, it loads the systemd and turn control over it. Systemd will then start the rest of the system. It is a Linux first process, parents to all other processes. This process is the first running process in any Linux or Unix system. It always has a PID number 1. So summary, as soon as you power switch on, all the initialization, the hardware component happens, and firmware, you have either BIOS or UEFI firmware, and you either one of these, and they take care of, there are two different mechanisms of loading the boot manager and bootloader. So UEFI has its own boot manager, like EFIND or BIOS, and then they load a different boot manager. And then if it's a BIOS, it goes for MBR, and MBR has section points to the first partition, active partition in the partitioning table, where you can find a second stage bootloader and so on. Once kernel loads and executes, it initiates the first process, and the first process loads other program and create a new process and threads, and that's on the operating system loads of your new device drivers and everything, and take control of the whole operating system from firmware. Thank you so much for listening, and if you have any questions or suggestions, feel free to contact me. Thank you.